Ray diagrams for diverging lenses. If rays come in parallel to a converging lens, the focal point is on the other side of the lens. That's what we call positive. For a diverging lens, rays coming in parallel appear as if they're coming from a negative focal point. So when we draw ray diagrams for ray 1 and ray 2, we have to account for that negative focal point. Let's draw diagrams now. Diverging lenses only produce virtual images, which will be on the same side as the object. For these ray diagrams, I will only consider 3 object locations, where the object is outside of 2F, the object is between 2F and F, and finally, the object inside the focal point. Let's draw the ray diagrams. I'm only drawing ray 1 and ray 2 in each of these situations. The way I draw the ray diagram here is that I first draw it parallel to the central axis. Now I start at the focal point and I go to where the ray meets the lens. Starting at the focal point, I draw a dashed line to that intersection. Then I finish it off by drawing the ray that diverges from the lens. Let's draw ray number 2. Ray number 2 starts at the tip, goes through the focal point, and you could see that these 2 rays now intersect inside the focal point but on the left side. The image then in pink here is erect, smaller, and virtual, where S prime, the distance from the lens to the image, is the image distance, and the object distance, S, is the distance from the lens to the object. As the object now moves between 2F and F, ray 1, diverging from the lens, following it back to the focal point, and ray 2, going through the center of the lens, produces a virtual image again that's going to be erect, smaller, but if I compare the size of this virtual image to the one from the previous case, you could see that it's grown in size. Let's go to the next case, where the focal point and the image is inside the focal point. Drawing the same 2 diagrams, or ray diagrams, drawing the 2 same rays, we see here that I have a virtual image that's now larger than the previous 2 cases, but the image is still erect, it's smaller than the object, and it's virtual. Next, I want to summarize all of these rays in one ray diagram. In summary, a ray diagram for all possible situations for a diverging lens, except for the point S equals F, I'm going to look at 3 locations. S equal outside of 2F, S between 2F and F, and then inside. Ray number 1 never changes. Let's draw that. We see that the ray is the same for all 3. Now it's ray number 2 that changes. For ray 2, you could see here that it crosses ray number 1 right here, and therefore produces its image. As the object moves closer to the lens, the green ray here, you could see it that I'm going to get a larger virtual image. When the object is inside the focal point, you could see here that this violet ray image is larger than the rest. So as the object moves towards the lens, you see the image move towards the lens and grow in height. In summary, all diverging lenses images are virtual. As the object moves closer to the lens, the image grows in height. This is the second lens diagram that you should be able to recreate on your own. I now want to use a Duffy applet for lenses where John Welch, our lab tech, made a modification to this thing. Duffy's converging lens applet is set up so I have a converging lens, but the way I draw it in lecture here is that I draw it with the straight line instead. The dark points are the focal points. The circular circles here are twice the focal point. This guy here is the object, and we could see that the object is outside of the two focal point location. And then the image is in blue here, and what you're seeing here is that I have three rays. I have a red, a blue, and a green. Now, what I want you to pay attention to here is that as this object moves inward, look what happens to the image. So here I go. So now if I move this guy inwards, you could see that the image moves from roughly the focal point on the other side, the far focal point, and it's starting to move towards the two focal point location. And it gets bigger and bigger until when the object reaches the two focal point mark, you could see that the image is the same size. But once I go inside the focal point, you could see that the image is getting farther away and it's getting larger. And it's getting larger and larger and larger. Now, to actually get you to see this a little bit better, I'm going to change the focal length of this lens. So when I do this here, you'll see here is that as I get closer and closer, the image gets much, 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 much bigger. And when this object gets to the focal point, look at the rays are then going to be parallel. So when I look at ray 1 and ray 2, they're parallel, and this is when we say that the image is focused at infinity. Remember the railroad track analogy that I gave you. Now here's this magical point. When this object crosses the focal point, we say that the image that was at infinity goes from positive infinity to negative infinity. And the reason why that is here is that there's a discontinuity in the equations that describe the location of the image. So as I cross it, you'll see that the image is now erect and larger, and always it's outside of the object location. So now, if I rerun this thing, moving a little bit faster here, let's summarize this thing. If I'm outside 2F, as I move in, we see that the image is getting larger and larger until at 2F it's the same size. As I go in between 2F and F, the image is growing larger and larger and larger. When I cross over the focal point, the image is now on the left side and virtual, and it's always bigger than the object. Now let's go to the diverging lens. So clicking on the diverging lens, I now have a diverging lens, and you could see here that they're showing all of the rays, but we only focused on the red ray and the blue ray, which is the red is ray number 1, the blue is ray number 2. So now let's do the same thing. As I move my object towards the lens, the image in blue here is tiny. But as I move it, we start to see that the image is getting larger and larger and larger. And as I bring it in, you can always see that the image is always inside the object. and always smaller. Only when you get to the middle of the lens are the object and image distance the same. In summary, this is what we know about converging lenses. An object starting outside of 2f and moving towards the lens has the image grow in height and move from outside the focal point to outside 2f on the other side. Images are always inverted and real, but their sizes change depending on the location of the image. The ray diagram is shown right here. So that means as I look at the orange, except for inside the focal point, these three diagrams see the image move out. You could see the blue, the green, and the violet. The only time that is not true here is when the object is inside the focal point. Let's write about that. Only when the object is inside the focal point does the image become virtual, erect, and larger. Now let's do the diverging lens. Diverging lenses that have objects starting outside of 2f and moving towards the lens will have the image also grow in height, and that image will always be inside the object. They always produce a virtual, erect, and smaller image.